Additional facts for Newton's third law of motion. Extra facts that people may enjoy. Isaac Newton did much more than create laws of motion. He studied light and color, invented an early form of calculus, and built a better type of telescope. Other work Newton did. Newton explained gravity in a way that helped scientists understand both falling objects and planetary orbits. His book Principia Mathematica shaped modern science. Scientists connected to Newton. Newton built on ideas from Galileo and Kepler. His work later inspired Albert Einstein. Edmund Halley supported Newton's research and pushed him to publish. Other things that people should know: Newton's third law shows up everywhere. It explains how rockets launch, how birds fly, and why walking works at all, or how walking works at all. Understanding this law helps people see how forces always come in pairs. Additional interests. Things that I personally found interesting while working on this project. I was surprised by how often Newton's third law shows up in everyday life. I never realized walking, jumping, and even breathing involve action-reaction forces. Also didn't expect pendulums to be such a clear example of equal and opposite forces at work. What I learned compared to what I expected. I thought I would only learn the basic definition of the law. I ended up understanding how deeply it connects to real motion and how deeply it connects to real life. Just like I was saying, I didn't, when I see somebody jumping, it compares. Where was I? Seeing how a pendulum transfers force from one ball to another helped me visualize the law in a way that I didn't expect. What I would have explored if I had more time. If I had more time, I would look deeper into how engineers use this law designing cars or aircraft. I would also explore more of how astronauts use this reaction in space where there's no gravity or air resistance, and how pendulum behavior exchange when gravity changes. Overall summary for Newton's third law of motion. Overall, the project went pretty well. Once I chose my examples and problems, everything started coming together. The most important part was understanding how Newton's third law shows up in real situations, because this made the whole project make sense. The easiest part was explaining the basic ideas and connecting them to everyday examples. The hardest part was creating a brand new numerical problem that was unique but still realistic, making sure that the problem was not too simple or too complicated. Took the most time. What surprised me was how many places that the law appears without us noticing, from pendulums to walking to cars pushing against the ground. Working through the project made the topic feel much more connected to real life than I ever could have expected. Relevant sources. So on the right side for me, I listed all the picture sources and the parts that they go to. And then for original source, I put for 1.4 part B. It's about Newton's laws, his background. That's where I got it from. Let's see. The source was useful because it gave accurate background information on Newton's life and career. It helped explain his discoveries and supported the section of the project where his influence was discussed. Like I said, the source was used for 1.4 part B, relevant scientists, to give educational facts about Newton and reliable facts. Then I listed 4 more sources, and that's all my sources.
Additional facts. Extra facts other people might enjoy. He was born on 2 dates. He was born in 1642 by the Old English calendar Julian, and which is 1643 by today's Gregorian calendar, so you'll see both in books. Other work Newton did. Wrote extensively about religion, biblical interpretation, and historical chronology, a massive chunk of his writing, even though it's less famous today. Scientists connected to Newton. Christian Huygens, an important contemporary in mechanics, astronomy, optics. Newton's work developed alongside and sometimes in tension with figures like Huygens, and Newton faced notable skepticism about some of his optical claims. Other things people should know: he did non-physics research too. Newton wrote a lot about theology and did extensive alchemy work. Huge parts of his papers, even if they're not what he's most famous for today. Additional interests. Things I found interesting. I found interesting how his jet propulsion worked and how jet engines and rockets use the same physics but trade massive differently. Jets move ton of air a little faster, rockets move less mass much faster. That's why jets are great in atmospheres and rockets are necessary in space. What I learned compared to what I thought. I thought Newton's third law would be mostly a simple slogan for every action, and jet propulsion would be basically exhaust goes back and rocket goes forward, but I actually learned the process is deeper. Propulsion is really momentum bookkeeping, and performance depends heavily on mass flow rate, exhaust velocity, and noise pressure matching. Well, I would investigate with more time. I would investigate how engineers measure how good a rocket jet is and what design choices raise efficiently. Overall summary. Overall, the project went pretty good and smooth. I learned so much about Newton's third law and how it's in everyday life. I think after I chose my example for Newton's third law, the project was a breeze because I was able to easily put the slides together. The most important part was really understanding how forces actually work in interactions and how it's the foundation of behind propulsion, collisions, and momentum conversion. I think the easiest part was choosing my example for Newton's third law I wanted my slides to be based off of, because once I fully understand the example, I was able to easily talk about the history and the connections to real life. I think the hardest part was coming up with a numerical problem because I had to make sure it was a real solution and that it wasn't too difficult. I was most surprised learning that equal force doesn't mean equal effect. Two objects feel the same force from each other, but the lighter one accelerates more because acceleration equals force divided by mass. Some relevant sources. Original source for 1.4 Part B. Original excerpt. Galileo Galilei was born in February 15, 1564 near Pisa. The son of a musician, he began to study mechanics at the University of Pisa, but changed to philosophy and mathematics. In 1589, he became a professor at the mathematics at Pisa. In 1592, he moved to become a mathematics professor at the University of Prusa, a position he held until 1610. During this time, he worked on a variety of experiments, including the speed at which different objects fall, mechanics, and pendulums. Why this source was useful? This source was useful because it gave me everything I need to know about the scientists Galileo Galilei, and gave me facts to be able to put into my slides. Where was it used? It was used in 1.4 Part B, A Relevant Scientist, to give facts and details about his life. And these are some of the sources I used for Part C and Part B.
On this slide, I wanted to share some extra facts about Isaac Newton that most people don't usually hear about. We always hear about the 3 laws of motion, but Newton actually lived a really interesting life beyond physics. For example, during a plague outbreak, he had to leave school and stay home, and during that time, he invented calculus. That shows how productive he was even during isolation. He also worked at the Royal Mint, where he helped redesign England's currency system and even helped catch counterfeits. Newton's influence also connects to other major scientists. He built on ideas from Descartes, and he often debated with Robert Hooke about light and force. Even their rivals pushed scientists forward. Overall, his work didn't just stay in physics labs. His laws are still used today in engineering, robotics, and space exploration. His ideas are truly universe. When I started the project, I didn't realize how many different fields Newton actually influenced. I was surprised to learn that he made a huge discovery in optics and basically created calculus. I also didn't expect him to have such a big role in Royal Mint. He wasn't just a scientist, he also helped protect the country money from counterfeit. Compared to what I expect to learn, I thought this unit would just be about forces, but it went much deeper. I learned how the impulse, momentum, and mass all interact during collisions, and how Newton's third law shows up in those measurements. If I had more time, I want to investigate how sports science uses the same ideas. Things like helmet design, pads, or safe sports equipment all rely heavily on impulsion and momentum. That connects between physics and everyday safety really caught my attention. Overall, this project went a lot smoother than I expected, but it also taught me more. I was able to connect Newton's third law to real experience and real data. Looking at both the historic background and the modern technology helped me understand the topic from two different perspectives. The part I found the most interesting was seeing how Newton's third law actually shows up in measurable ways. Calculating momentum and final velocity made the law feel real, not just something you memorize. The easiest part of the project was describing the historical and modern lab's environment, but the hardest part was making sure my new problem was completely unique and explained every calculation step clearly. One of my biggest surprises for me was realizing how much modern technology still relies on Newton's third law. From rockets to cars to even sports gear, it made the law feel relevant to real life. These are my main sources I used throughout the project. Each one supported a different part of my research. The NASA page helped me understand Newton's law in a way that relates to aerospace and motion. The Science of the Day article helped me learn more about the scientist's connection to Newton's, which added context to his work. The most helpful source overall was Hyperphysics. It explained Newton's third law in clear language and used diagrams that look very similar to the steps set up in our experiments. The source helped me understand force, action, reaction pairs, and momentum during collision. I use these sources to support multiple sections, including the explanation of the law, the original and modern lab process, the numerical problem, and the verification steps. They provide the reliable information I needed to connect everything together.
Facts. So the law statement: for every action there is an equal and opposite reaction. Historical context: first formulated by Sir Isaac Newton in Philosophiae Naturalis Principia Mathematica in 1687. Has applications in engineering, rocket propulsion, exhaust gases push backward, rocket moves forward. Airplanes, wings push air downward, and air pushes wings upward, and they lift them. Everyday examples: walking, foot pushes ground backward, ground pushes foot forward. Rowing, the oar pushes water backwards, water pushes boat forward. Other scientists: Newton influenced later physicists like James Clerk Maxwell, electromagnetism, and Albert Einstein in relativity. Additional interest. Surprising discovery: the law explains why motion is always mutual and that no force exists alone. Interesting realization: even tiny interactions like pressing a wall involve equal force, though the wall doesn't move because it's massive inertia. What I learned versus expected: initially thought the law was only about collisions, but research showed it governs all forces: gravity, electromagnetism, friction, all of it. Future investigations explore how Newton's third law applies in space in the microgravity environments. Study how it connects to conservation of momentum in particle physics, and investigate modern applications in robotics and biomechanics. Overall summary: I think the project went really, really well. There's a lot of stuff that I did not know about Newton's third law that was brought to light. It revealed its universality, and it applies to every force interaction. The most important part to me was that the law ensures balance in nature. Without it, motion would violate conservation principles. The easiest part for me was finding everyday examples, for instance, the walking, swimming, jumping. The hardest part for me was connecting the law to abstract fields like quantum mechanics and astrophysics. Honestly, the most surprising was realizing rockets work in space without air purely because of Newton's third law. And these were all of my relevant sources, and there's the pictures where I found them, or that's not all of them, that was just some of them, and then the links to where they go.